All right, so continuing on with this. So what mathematicians have done have defined a function called the air function, which is basically the area under this curve. It is air function for any value, like 1, 2, 3, or 4. So the way you do that is you take e to the negative x squared, and you go out to some value. You get the area under the curve. That's what that integral represents. And then you multiply it by 2 divided by the square root of pi. So if we just thought about how it worked, what if we were trying to get air function 0? That means we would integrate from 0 to 0, and that's going to give us 0, and multiply by 2 divided by the square root of pi, and that's going to give us 0. So the first point on this function is going to look like that, of air function w, something the mathematicians have defined. All right. If you go out to a really, really large number, okay, so air function of a large number, say like 10 or something like that, well, you would do 0 to 10 e to the negative x squared. Amazingly, that is almost the square root of pi over 2. If you actually went out to infinity, it'd be the square root of pi over 2. Take almost the square root of pi over 2 and then multiply it by 2 divided by the square root of pi, and you're almost to 1. So as you get to large values, this function, I'll get my asymptote up there, gets really close to 1, and you get a function that actually rises and then approaches 1 and gets closer and closer to closer. So it's very much like some other functions that you've had, but the exact numbers are a little bit different. So for a lot of us, that's probably a new function, air function w. And how does it apply to the plane wall? Well, it turns out that solution of the equation involves the air function, and this air function tells us essentially how much temperature rise we have within the wall at some point. All right, give me a second and I'll get the solution of the equation then that people came up with. So going back to that original equation that we had, okay, original differential equation. Okay, that original equation, if the physical situation we were looking at was a plane wall that was very, very deep, okay, very, very deep, deep enough that the temperature effects, say like that 700 degrees C that I was talking about at the surface, doesn't really penetrate all the way in. The term that the book uses for it, they called it a semi-infinite solid. Then our function, txt, that's what we're looking for, is given, let me write it down for you guys really quickly. Is given by this equation right there. So going term by term. Ti stands for the temperature the wall started at. Ts is what the surface temperature rises to all of a sudden, say 700 degrees C. Okay, and then this is the air function, and if you're trying to figure out the temperature at any position, any time, you put your position within the wall from the left side in as x, and this is the square root of alpha t. So sorry about my writing; it's a little bit messy, but nonetheless, that's the equation that we end up using. The book ends up doing some algebra and simplifies it, so I'll show you the book's version really quickly. Okay, so the book simplifies it. These two equations are equivalent, okay? And what they're saying is that if we have a case where we have a really deep wall and all of a sudden the surface temperature rises to some value, and we want to go to any interior point within the wall and figure out this temperature at some point in time, well, we can just plug the numbers in here and use our air function. All right, how do you figure out these air function numbers? Well, first of all, some calculators actually have the air function on it, and finally some programs on your computer have it, like Excel has the air function in it. If you want to use the book, in appendix B in the book, there is an appendix where it gives for any value you put in to these parentheses, it'll give the air function. All right. Well, why don't you guys give me a second and I'll set up we'll try to apply the air function or this solution to a heat shield type problem. And we're going to do it in this form right here. So we're going to try to solve that equation right there. All right. Give me a second to set it up. So we're going to have a heat shield, and it's part of some sort of capsule that's re-entering into the atmosphere, and we're going to say that the heat shield is 25 centimeters deep. Okay, and initially its temperature is 20 degrees C the whole way along, and at the left side where it's rubbing against the atmosphere, it really quickly jumps up to 700 degrees C. So there's the side that's rubbing against the atmosphere. Over here is the interior of our capsule, and here's some sort of material that's done as a heat shield. And it's pretty interesting to look at all the different materials that have been tried over the years for heat shields. I'm going to go with the ceramic. Ceramics are pretty interesting, and the properties that we're going to use for this ceramic are, I'll get up on the board, pretty conductive, 13 watts per meter Kelvin. Okay, pretty dense, 1,300 kilograms per meter cubed, okay? And then finally we need to know its specific heat, and we're going to go with 2,000 joules per kilogram Kelvin. Okay. All right. And then finally the time we're interested in is going to be 8 minutes. So let me get that information up there, okay? So we are going to say like 8 minutes after this process starts, where all of a sudden this side over here gets up to 700 degrees C, what is the temperature distribution inside there? And we're going to try to apply this equation right here. We don't need to use the other form, so I'm going to get that off the board. All right. So looking at applying it, thinking of what we're going to fill in for our numbers, TS is going to be 700 degrees C, so I'll just put that number in there. TS minus TI, well, that's going to be the surface temperature, which was 700. I'll get that back up there. And the interior surface, the initial temperature that the whole wall was at was 20, so that's going to be 680. Okay, so for this particular application, T at xt is 700 minus 6080 times the air effect function of some sort of value. And thinking about what we're going to fill in for this, we're going to make a chart where we're going to get the temperature after 8 minutes at 0, 5, 10, 15, 20, 25, and see how it works out. And I want to expect you to do all that work right now. I'll give you some of those values, how they turn out, and see if we can make sense of it. All right, T, we got it, 8 minutes, 480 seconds. But alpha, that's the thermal diffusivity, so we should take a second and calculate that on the side using the information given. So one thing we'd like to know, thermal diffusivity, alpha, kind of gives you a sense of if there's a temperature change within a material, how quickly it spreads out. So that you would get by doing K over rho C. You can try it on your calculator, and it turns out that alphas in general are really small. It's 5 times 10 to the negative 6, and the units are meters squared per second. So that can be thought of, that alpha can be thought of as telling you, hey, the temperature change that is occurring over here would, if it could spread out in a circular area, would spread out 5 times 10 to the negative 6 meters squared per second. So gives you a feel for what that means. That's not very precise. All right, so we got our alpha. We can go ahead and get to work and set up a chart. So a chart might look something like this. We're going to have 4 rows. Okay, so let me see what I got going on so far. Okay, so to work our way through this equation, one thing we're going to need to do for every x is we're going to have to calculate this argument of the air function. So that's what I got going on here. I'm going to, at x equals 0, I'm going to do that argument. I'm going to call it w. W equals x over 2 times the square root of alpha t. And then I'm going to look up the air function of that w, and then I'm going to do the math and solve it. Okay? And I'm going to do it for 0, 0 0.05, all the different positions in the wall. 0.05 would be meters, and of course that would represent 5 centimeters. So give me just a second to set this up. Okay. All right, so the first column, evaluating this is pretty easy for the first column. If I put 0 in there, of course that's 0, and then I can take that from there. But what about 0.05? Well, you just have to plug and chug on your calculator. 0.05 divided by 2 times alpha times t, the square root of all that. And I've worked that out before, so I'll get that number up there. It turns out that it is going out to a couple decimals, 0.56. Okay, all right. And then what's going to happen to this argument of the air function as x increases? It's going to keep getting larger and larger and larger. So I had 0.56 here. Now it's 0.10. It should be larger. In fact, it should be double. So it's 1.12. I skipped 0.15. So I'm going to go to 2.24. And 0.25 is 2.80. Okay. So those are just calculations, all right? All right, so how about the air function? The air function, well, you can look it up in the table or you can use your calculator. Remember that air function is something that as this gets larger, it gets closer and closer and closer to 1. Air function 0 is 0, so we know that. Over here at 2.80, we're hoping we're getting close to 1 because then the math is going to turn out that this temperature over here, this final row right here, is going to be 20 degrees C. And that's what we would like. We would like it to be really cool on the interior of the wall. All right, well, I'll give you what the air function's values are. And you could try it out on your calculator or look in the appendix or use Excel. Okay, so here we go. Again, we're hoping that as we get towards the interior of the wall, that this air function computes to about 1. That would mean that if you think about what this equation here is saying, okay, that actually, this air function is telling us how much of the total possible rise is still left. The wall started at 20. The left side is 700. That's a total rise that's 680. If this side over here stays at 700 and then heat keeps flowing in, eventually the whole thing could rise to 700 degrees C. Okay, but this air function tells us how much of that 680 rise is left, and this is basically saying 100% is left. This number over here is saying 100% is left. There's hardly any rise over on the right side of the wall. All right, so what we're just doing is for every, we're just plugging the numbers in. We're plugging this air function number, this air function value for all of those. And let's take a look at how the temperatures look. Okay, give me just a second here. Okay, so, the left side of the wall is 700, and that was essentially part of the problem statement. Because of friction with the atmosphere, the left side rises up to 700. Okay, 5 centimeters in, temperature's really risen. It's up to 312. Really, really hot. We wouldn't want to be anywhere near that. 10 centimeters in, 97. Still pretty hot. Something that we never would want to actually touch. Okay, but then how about 20 centimeters in? It's risen a bit. Okay, it's risen a bit. And then finally, as we get into 25 centimeters in, it's risen hardly at all. So what these numbers would be saying is, hey, if we went with a 25 centimeter heat shield with those materials, okay, Surface, because of friction, rises to 700, and we make it 25 centimeters thick. The heat is hardly going to penetrate into the inside at all. We've done a good job sizing our heat shield. If instead the reentry time was larger, maybe double that time, then this temperature over here is going to start rising pretty significantly, and we would need a thicker heat shield. Okay, great. Well, that's it for the case where you have a semi-infinite solid, where it's a one-dimensional wall and we're trying to get heat going into that wall. You're welcome to look at all the other different cases that are in section 5.7 and chapter 5. It's a pretty fascinating topic of ways people have figured out about computing those different temperatures. I encourage you to give the optional problem on chapter 5 a try. On homework number 9 a try. And please let me know if there are any questions on it. Have a great Thanksgiving. Take care, guys.